this presentation related with the subject fundamentals of surface engineering. And in the previous presentations we have talked about the other thermal spray processes, and more specifically the flame spray process. The flame spray process is known as the high temperature low velocity process, and which suffers from the various undesirable features like coarse grained structure, porosity, inclusions, and a limited bond strength. So we have also talked about the few methods which can be used to enhance the performance of the flame spray coatings. In this presentation we will be talking about the three processes. These are the high velocity oxy-fuel spray process, detonation gun spray process, and the cold spray process. All these three processes are the combustion based processes where fuel oxygen gas mixture is burned to generate the heat, and then after accelerating the particles to sufficiently high velocity, the impingement of the coating material with the substrate takes place for the development of the coatings. So these three processes primarily differ with regard to the velocity which is attained and the temperature up to which material is heated during the spraying process. So we will be talking about each of these processes one by one. Like say if we see the comparative plot of the various thermal spray process, then the particle velocity and the gas temperature, these are the two very crucial parameters. The temperature which is generated during the thermal spray, and the particle velocity which is attained during the thermal spray. So particle velocity decides the density or the soundness of the coating as well as the coating substrate bond strength, and the kind of the splat to splat bonding is also influenced by the particle velocity. On the other hand, the temperature of the heat source or the gas temperature or whatever is generated during the thermal spray process, that may cause complete melting of the particles which is being sprayed, and or it can cause the partial melting, or it can cause just the thermal softening of the materials. So in case of the cold spray process, the temperature, gas temperature is very limited, and the particle temperature is also like 400 to 500 degrees centigrade. So there is no melting as such, and primarily the thermal softening of the material takes place, while in other processes the temperature rises more. Like if we see the arc wire spray process, the temperature is in the range of 2000 to 4000 degrees centigrade, while in case of the plasma arc spray process, temperature can be even greater than the 5000 degrees centigrade. For detonation gun, temperature is low, like 2000 to 2500 degrees centigrade. The same is true for the high velocity oxy-fuel spray process, but it is higher than cold spray process, like 1000 to the 2200 degrees centigrade. But these are the flame temperatures. The particle temperature will in all these cases will be lesser, and since higher the flame temperature, so greater will be the particle temperature, and which will be leading to the either melting, partial melting, softening tendency. But apart from these, there will also be tendency for the interactions of the material which is being sprayed with the gases which are present. So this will be affecting the soundness, especially with regard to the inclusion formation. And the second one, kind of the metallurgical transformations metallurgical transformations. Sometimes undesirable metallurgical transformations can degrade the quality of the coating material which is being sprayed, especially like W2C, like tungsten carbide can transform to the WC. So this is of the higher hardness of 25 HV, while this may be of 1800 to 2000 HV. So this kind of the thermal degradation can occur if the coating material is exposed to the higher temperature for longer time. So if we consider these two aspects, then we'll notice that those processes where temperature is limited, they will be favorable with regard to the inclusions formation or the undesirable metallurgical transformations point of view, while the higher particle velocity will be leading to the more dense, less porous, and the good coating substrate bond strength. And apart from that, when the particle velocity is too high, then it will be leading to the development of the residual compressive stresses, and this is found to be favorable under the wear conditions, as well as this can also be helpful in enhancing the mechanical performance of the component. So if we see the more thermal damage will be occurring in case of the arc wire spray and the plasma arc spray processes, but the wire flame and the powder flame spray process, these are the very low velocity processes, while in case of the detonation gun, high velocity, and cold spray process, these are the high velocity processes, and so they will be leading to the much better coating substrate bond strength, development of the residual compressive stresses, as well as reduced porosity in the coatings. Now we will see the particular process in detail. So the high velocity oxy-fuel process. So here oxygen and fuel gas. It can use number of fuel gases. It may be in form of, like, say, the propane, hydrogen, acetylene, liquid petroleum gas, ethylene, kerosene, methane, etc. And all these we can select one of these fuel gases mixed with the oxygen, and then it is fed in the torch so that the flame can be produced. So we can see the oxygen is fed, and then we'll see also that the fuel gas is also supplied. So oxygen and both fuel gases are supplied, so that after forming a mixture, their combustion can take place, and sufficient heat is generated, and the temperature rise takes place like 2000 to 2500 degrees centigrade, and this one is needed for either melting or partial melting of the material which is to be coated, and the material which is to be coated is fed with the help of suitable carrier gas, which may be in form of, like, say, the nitrogen. So the material in form of the powder may be, like, say, the nickel, chromium, boron, silicon, or the cobalt, chromium, tungsten, carbon, or the nickel tungsten carbide powder mixture. So as per the need, suitable material is selected, and it is fed with the help of the nitrogen as a carrier gas. So when it passes through this one, the very high velocity is attained due to the heat generation, as well as the compressed air is also used. So combination of these things will be leading to the generation of the very high velocity of the gases as well as the particles which are there. So it will be, like, say, 500 to 1000 meter per second powder velocity. So if we see in this case, oxygen and the fuel gas mixture is being burned, at the same time we are also using the compressed gas, and the powder is fed with the nitrogen as a carrier gas. Earlier we had just used the oxygen and fuel gas mixture, and in that one we had fed the powder mixture. So because of the additional role of the compressed air along with the oxygen and fuel gas mixture and the feeding of the powder with the help of the nitrogen as a carrier gas, all these things will be facilitating the suitable supply of the coating material in the flame, which will be heated to the sufficient high temperature. Then it will be accelerated, and when it is accelerated to sufficient high velocity, the impingement of this material with the substrate will be leading to the development of these coatings. So we can say this is an advanced version of the flame spray process, and a very high velocity up to 1000 meter per second can be attained by the powder particles which are being sprayed onto the surface of the substrate, and the temperature is also high enough to cause the either melting or the partial melting. Since the velocity which is attained in this process is quite high, and that is why the impingement of the powder particles with the substrate will be occurring at a very high velocity with a high kinetic energy. So it will be getting flattened very firmly, and that is why the pores which are left out between the coating and substrate, or between the various splats, these are very less, and that is why we find very limited pores. So the porosity in these coatings, in HUF coating, is less than 1%, and high velocity impingement with the surface of substrate or already deposited material will be leading to the very good coating substrate bond strength greater than 80 MPa. We know that minimum acceptable coating substrate bond strength is 70 MPa, but when this process is effectively applied, we get much higher coating bond strength. Since the particle velocity through the flame is extremely high, so the material stay of the material during the flight from the torch to the substrate is very less. So duration, especially the duration of the coating material in the flame, is for very less period, and therefore the kind of thermal damage in terms of the undesirable metallurgical transformations or the interaction of the coating material or material to be coated with the gases which are present, all that is very less. So what is important, the duration of the stay of the material being coated at a high temperature is less in HUF process because of the high velocity, and that's why the thermal damage in terms of the undesirable metallurgical transformations or interaction of these materials with the gases is very less, and that is why we get extremely reduced damage to the material which is being coated onto the surface of the substrate. And like say particle velocity, particles of size 10 to 63 micrometer can attain the velocity in the range of like 300 to 800 meter per second, especially at the time of impact. The kinetic energy of the powder particles at the time of impingement is more crucial. So that in turn also will be affected by the standoff distance which is between the nozzle to the substrate. So it has to be optimized so that the particles attain the maximum velocity, and at the time of impingement the particles are having the enough velocity, and this kind of the process can be effectively used for coating wide range of the materials, which can be used for enhancing the abrasion resistance, erosion resistance, and since the deposition rate offered by this process is very high, so it can be effectively absorbed for at the industrial level for surface modification, so that the resistance to the wear under the different conditions can be enhanced. And considering the application, the HUF is effectively used in the energy generation sector, like say in thermal power plants, in hydro power plants, like the hydro turbine blades subjected to the slurry erosion. So if they are coated using the suitable materials, then they will be able to effectively reduce the erosion. Similarly, high temperature resistance is needed in case of the thermal power plant. So erosion resistance at high temperature is important for thermal power plants, and for that purpose, like thermal barrier coatings are used, which will not only be reducing the temperature of the main component but will also be increasing the erosion resistance. These are also used like in cement industry for resisting the abrasion as well as erosion, and automotive industry and many other industries for enhanced wear resistance of the component. In the next slide, I will be showing the typical HVF spread coatings of the cobalt chromium carbon tungsten system. And if we see, this is the macroscopic image of HVOF coatings of this material. This is the cobalt based material, which offers very good abrasion resistance as well as the erosion resistance. And we can see here this coating thickness is about the 200 to 250 micrometer, and this is the coating is developed onto the surface of the mild steel to investigate what kind of the wear resistance. So if we see, hardly we have hardly there are major discontinuities, very fine pores are there here and there, and the if we quantify these pores are very fine, and these are very less in terms of the percentage. And further closer look, if we see for microscopic observation, then we can see there are a lot of splats in the form. So these are, we can say, these are the flattened particles which have been deposited over the surface of the substrate. So these microstructural features are completely different than what we normally observe in case of the conventional crystalline material systems. And here primarily we can see if there is there are discontinuities, so indicating the soundness, or what kind of the splats are being formed and what kind of the bonding is there between them. These are the kind of the microstructural features which we can observe. These features are completely different as compared to that what we get in case of the conventional spray processes or the conventional materials, where the fusion followed by the solidification. Now we will see the second process. This is called a detonation spray process. This is the another high velocity spray process, wherein the velocity of the gas is too high, like 3000 meter per second. The temperature is 3000 degrees centigrade, but since the velocity is very high, and that is why we notice that the stay of the particle at a high temperature is for very limited period, and that is why exposure of the material being coated is for very less time. And since the time is less at a higher temperature, time of exposure at a high temperature is less and therefore the associated the thermal damage to the material being coated is also less. That is why, despite of high temperature, since the velocity is high, so the exposure is for the less period. And in this case only if the material is being sprayed by the detonation spray, high velocity will be leading to the limited transfer of heat to the powder particles. So only the surface layers will be brought to the molten state, while core remains in the solid state. So only this is the situation of the partial melting. And in this case the core is just the thermally softened which is favorable especially with regard to the development of the residual compressive stresses. So, how does it work? In case of the detonation spray, we have to feed, as I said, this is another combustion based process. So, we have to feed oxygen, we have to feed acetylene, and this mixture is burned or detonated by giving the spark through the spark plug in very controlled way. So, like say the mixture is fed through these controlled like oxygen and acetylene is fed through these control valves, and then this mixture is detonated with the help of the spark plug, and as soon as detonation takes place, powder is fed in this barrel, and so whenever this detonation happens, the high velocity gases will be moving towards the exit along with the powder particles, and these powder particles during their travel through this barrel will be heated to this partial melting or thermal softening conditions, and once these come out, they will be directed towards the surface of the substrate where these are to be coated, and this distance is of like say 50 to 100 mm. So, the barrel to the substrate distance is about 50 to 100 mm, and after each like say after each detonation, like for each detonation we feed the oxygen and acetylene, spark plug will be detonating it, and then powder is fed, the matter and all the gases as well as powder mixture will be directed towards the surface of the substrate, and once this cycle is completed, the purging is performed of this gun barrel with the help of nitrogen. So, all those burned gases and the powder which has been fed can be cleared from the gun, and the next round of the detonation is carried out. So, this process of the detonation is repeated number of times. So, number of detonations in this case may vary like say 1 to 10 number of detonations per second, and this will be determining the rate at which the coating thickness will be increased. Obviously, greater is the number of detonation per second, higher will be the rate at which the coating thickness will be increased. So, that is what has been explained in these points, like the mixture is fed, spark plug will be detonating it, powder is fed, and once the things are accelerated towards the substrate, and then material is deposited onto the surface of the substrate, and then just to clean up the things, the nitrogen purging is performed, spark plug performs the detonation of the oxygen and fuel mixture, powder feeder is used to supply the powder in very controlled way in the gun barrel, so that we can deposit the material at the required rate, and the detonation can happen at a particular frequency of 1 to 10 number of detonations per second, which in turn will be affecting the thickness, the rate at which thickness is being increased, and then since the velocity of the powder particles which is attained during the spray process is very high, and that is why, since these powder particles where just a surface has been brought to the molten state and the core has been softened, and when the impingement of these particles happens at very high velocity, then it will be leading to the flattening with the very firmness and with very soundness, and it will be leading to the reduced pores and very increased coating substrate bond strength. So, this is the good side associated with this process, that high powder particle velocity of 800 to 1000 meter per second, leading to the very sound coating substrate bond strength, reduced porosity, and at the same time, since the coating material is getting flattened in the solid state itself, that is why it will be under the plastic strain conditions. So, when the material is flattened under the plastic strain conditions, it develops the residual compressive stress. So, whatever coating is developed through this process, the coating at the surface has the residual compressive stress. So, because of the high velocity and limited heating or only the surface layer, melting facilitates the reduced porosity, good bond strength and residual compressive stresses. And these now the one typical result for the detonation spread material here these are the two micrographs which show that the nickel chromium material of the powder particle size 40 micrometer is spread over the surface of the substrate having the spot diameter of the 25 mm, and the detonation spraying was carried out at the rate of 4 shots per second for developing the coating of the 300 micrometer. Then we get the coating structure of this kind, and here this is the low magnification structure of the coating, which shows that coating is by and large sound and free from the defects. However, some of the limited bonding at the interface can be seen, but this is primarily because there is no fusion of the interface, fusion of the substrate and the coating. Only the surface layer of the coating material powder is brought to the molten state. But if you see the closer look of the coating, then these splits can be clearly seen, which has been deposited over one over other, and still some of the micropores can also be seen here and there. Since this process there is no complete fusion of the powder particles and primarily high velocity, only surface layer melting of the powder particles leading to the very sound coatings with very good bond strength, and that is why this process does not suffer any kind of the thermal damage and thermal degradation, especially with regard to the formation of the inclusions or formation of the undesirable metallurgical transformation. So, this is how we can say this detonation spray process can effectively be used for depositing the variety of materials without any thermal damage while developing the sound coatings, which are with very limited pores, very good coating substrate bond strength. Now, I will summarize this presentation. In this presentation, basically I have talked about the processes. One was the high velocity oxyfuel spray process, which leads to the higher temperature as well as the higher velocity. In case of the detonation spray process, also the velocity is very high and the temperature rise of the coating material is very limited. Thank you for your attention.